Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today we are going to study how to solve the problem for your overhanging beam in relation to the concept of point of contraflexure. What is point of contraflexure? The point of contraflexure means the point where the bending moment changes sign from positive to negative. That point is known as point of contraflexure. So what it will happen at where that point of contraflexure? So it is a positive bending moment from up to the span, up to that point, left side becomes a left side or right side, it becomes a positive bending moment or negative bending moment. Whereas it comes to the another side of the point, the direction becomes negative bending moment. Suppose if the left side is positive bending moment, then from that point onwards, the bending moment changes to the direction to negative direction. Or if the bending moment on the right side is positive, then it goes to left side, it becomes negative. So these are the point of contraflexure is all about. So in this problem, we can see how the point of contraflexure, what is the point of contraflexure, how to calculate shear force and bending moment values in order to draw the shear force diagram and bending moment diagrams. This problem is subjected to UDL, uniformly distribution load, and point load. The supports are knife edge support and another one is roller support. Wherever the beam is supported by knife edge support, there will be one reaction. It can become upward direction or downward direction. And wherever roller support is acting, support is there where only one reaction acts, it can be either upwards or one downward direction. But in order to calculate the shear force and bending moment values, we need the known values of support reactions. So to find out the support reactions, what to be done? We have to use equilibrium equations. There are two equilibrium conditions we are going to use it in order to calculate the support reactions at point A and point C. So what are the support reactions are? At point A, it is the C here. At point A is RA. And at point C is RC. How to calculate these two reactions? We are going to calculate these two reactions with the help of sigma FV equal to 0, that is algebraic sum of all vertical forces, equal to 0. That means upward forces equal to downward forces. And another reaction, that is another condition, is algebraic sum of momentum equilibrium about any arbitrary point equal to 0. That means about that point, the clockwise moments or anti-clockwise moments equal to clockwise moments. So by using these two equations, we are going to find out two unknowns, RA, support reaction at point A, and reaction at point C is the RC. So we are using here upward forces equal to downward forces, that is AY plus CY equal to 10 into 4 is 40 plus downward 20, 40 plus 20, that is 60 kilonewtons. This is sigma FV equal to 0. Next, we are applying the moment equilibrium, sigma MA equal to 0. Now what is the MA equal to 0? That is CY, the reaction is clockwise, or that is a clockwise or counterclockwise movement. Counterclockwise movement equal to clockwise movements. The counterclockwise movement is CY into perpendicular distance, that is 8 meters. CY into 8 equal to 10 into 4 converted into concentrated load, which is acting at the mid length of UDL, that is 2 meters. So 10 into 4, that is 40, 40 into 2, yes, 40 into 2 plus 20 into 10, that is 10 meters span. The distance from moment arbitrary point A, point D to point A is 10 meters. So 280 by 8, that is 35 kilonewtons. Now from this CY equal to 35, what is substitute the CY value in equation 1? We will get it AY value, support reaction, that is AY is 25 kilonewtons. So AY equal to 25, CY is 35 kilonewtons. AY equal to 25, CY equal to 35 kilonewtons. How to find out shear force at various points by using shear positive and negative shear force sign conventions. Now let us begin. At point A left, it is 0. At point A right direction, that is upward, that is positive, that is 25 kilonewtons. At B, there are some, these two are acting at point B. Shear force effect is there. That's AY upward plus minus downward direction. 10 into 4, that is 40. 25 minus 40, that is minus 15 kilonewtons. Up to C, this minus 15, C left. If you come crossing C right, again minus 15 plus 35, that is 20 plus 20 kilonewtons. Then FD right is 20 and FD left is 20, continues constantly acting, and after crossing FD, then it becomes nullified, that is 0. That means the system is completely in equilibrium. How to draw this? By using these values, shear force diagram. Let us begin. Where the UDL is acting on the beam, that means it is linearly changing shear force. So up to at point A, it is 25 plus 25. Point B minus 25. That means point A to B, it is linearly decreasing, minus 15. Again, minus 15 is constant. So minus 15 is from minus 15, this is acting up to point C. So it is constantly, it is remaining constant. That is the point load. There is no load acting here. At point C, it is changing to plus 20. So it is increasing, and plus 20 is remaining constant up to point D. Thus here, wherever uniformly distribution load is acting, where the shear force is linearly, first order curve it is following, and there is no point load, that point load remains constant. Wherever point load is there, it increases. Again, it follows the constant formula, constant law. So thus we can draw the shear force diagram. So next, how to draw the bending moment diagram. So before going to start, next bending moment diagram, we have to follow the bending moment law, bending moment sign convention. This is the point positive bending moment and it is negative bending moment. So at point A, bending moment is 0. At point B, this A is acting upwards and UDL is acting downwards. So AY plus AY, that is AY into 4 meters, that's a positive, that is 25 into 4, minus this is 10 into 4 into 2, that is negative, that is 20 kilonewtons meter. And at C, that is 25 into 8, that is 8 AY into 8 meters. 10 into 4, this is the distance, this is the 2 meters here, 2 plus 4, 6, minus 10 into 4, 6, that is minus 40 kilonewton meter. And again at point D, it is 0. So now how it is changing, if we draw the diagram, yes, at A 0 and A to B is a point, this uniformly distribution load that is following second order curve, that is parabolic law, up to point C, at point C minus 40, and again minus 40, and at D it is 0. Now if you want to find out, this is the point here, positive to negative bending moment is changing here. This point with the baseline, that point is the contraflexure point. That is the point of contraflexure. How to calculate point of contraflexure? Let us assume, so point of contraflexure can be determined and put part BC equal to 0. Part BC, wherever BC, that is taking equation, then that is 5.33 meters from A. We can understand that from point A to, it is equate moment, at that moment, point moment equal to 0. Equate this equal to 0, then we can find out that X value, that X is 5.33 meters. So from support A, at a distance, at a span of 5.33 meters, bending moment is 0. That point is the point of contraflexure point. This is the point. It is 5.33 meters. So thus we can calculate point of contraflexure for a overhanging beam. So from this, what we can interpret it from shear force versus bending moment diagram. Yes, here shear force, in this case it is 0. That is not a point of contraflexure. The point of contraflexure is only considered for bending moment diagram. So wherever shear force is 0, that is minimum, the bending moment is maximum, that is 31.25 meters. Now Here the remains constant, but point of contraflexure, the point where the bending moment changes sign from positive to negative or negative to positive, but where the bending moment is also considered as zero. Thus we can understand the concept of point of contraflexure. Thank you so much.
Like, share and subscribe. Hit the bell icon for more updates.